Hello everyone. We want to do an example on true resistivity. So we discussed this equation, the saturation equation or Archie's equation, which SW is equal to root n, which n is a saturation exponent, and under the root we have A RW phi to the power of cementation factor multiplied by true resistivity. This is a very important equation, which we call it Archie's equation. So what we're going to do is to do this example. We have a sandstone core sample with diameter 1.9 centimeter. The length is 3.2 centimeters, saturated with brine, and the brine resistivity is 0.55 ohm meter. The core was desaturated in steps. It means that the water saturation is dropped step by step. If you look at the table, you can see the saturation starts at 1, which means 100% fraction, and it goes down all the way until we reach 0.3, which is 30% water saturation. So the core is desaturated with a method, and the resistance was measured, and these resistance are reported on this table. Please notice this is resistance, right? This is not resistivity. Look at the unit is in ohm, right? Not ohm meter. So what we want to do is to estimate the Reich porosity. So the first thing we want to do is, in our equations we don't have resistance, but we do have resistivity, right? So you need to add another column here to this table, and in this column what you want to do is to calculate the resistivity in ohm meter, right? The unit is ohm meter. So that's what we want to do, and it's pretty straightforward because we have the relationship between resistivity and resistance. It's RO multiplied by cross-sectional area divided by the length of the core sample. So if we do it for the first data point, that's 521 multiplied by the cross-sectional area. If you do the calculation, you'll get 2.835 multiplied by 10 to the power of negative 4 divided by 0.032 in meter, right? That's in meter. So RO is equal to 4.6162 ohm meter, right? So here is 4.6162. So you have to do it for all these data points and calculate all these resistivities, right? So that's the first step to do it, right? And the next step is to calculate the formation resistivity factor. So formation resistivity factor, you can use RO, right? F is equal to RO divided by RW, right? Now, it is mentioned, something confusing about this is basically here it's not actually RO, this is RT, and these values are total resistivity. Why am I saying that? The reason is that look at the saturations. Saturations are not 100%. If your water saturation is not 100%, then you're not really measuring the RO, you're measuring RT. So all these values, or I should say all these values except the first one, are basically the true resistivity, RT. The first value, however, because the water saturation is 100%, this is RO. Okay, this is very important. RO is the resistivity of the core sample 100% saturated with water, which is the first data point of this table, right? And the rest of the data points are RT values, right? So you can see I used RO using the first data point, right? And I measured capital RO. Now, whatever number you measure here, they are RT at that specific saturation. So RT depends on the saturation of the water. RO is at 100% water saturation, and that's a constant number, right, for that specific sample, right? But for the same sample, if you change the water saturation, your true resistivity would change. Okay, so I'm using the first data point, which is the resistivity of the rock 100% saturated with water, to calculate my formation resistivity factor. So in this case, it's 4.6162 divided by 0.55, and that is equal to 8.393. And I can use this, I can use the Humble formula, right? Either of those Humble formulas, if it is mentioned to you which one, you can use that one. If not, you can use either of equations. 0.81, for example, I use this one, divided by porosity squared. So porosity is equal to square root of 0.81 divided by formation resistivity factor, which is in this case 8.393, and the porosity will be equal to 0.31, right? So which means that your porosity is 31%. The next step is to calculate the saturation exponent n. It mentions by conventional technique, which means that you have a couple of data points and you want to use those data points to calculate your saturation exponent, right? So one thing you need to do is to calculate RT for all these data points. Okay, so for example, for this data point, RT is uppercase, basically R, or capital RT, is equal to RT multiplied by cross-sectional area divided by length, which is 678, multiplied by the same cross-sectional area values that we use for RO, 10-4, divided by 0.032, which is in this case is equal to 6.007 ohm meter, right? So you have to do this for all these data points. Calculate all the RT values, right? And once you calculate for each RT value, what can you calculate? You can calculate IR, right? So let's call this RT1, data point 1, basically RT1, and this is going to be IR1, so that's for that specific data point, and IR is equal to RT over RO, right? So 6.007 divided by 4.616, that is equal to 1.301, right? So you can calculate, so you will have basically another column here with all the IR values. For each of these RT values, right, you will have one IR value, right? So your table would look like something like this. So I don't want this. So I think I can write here now. So you will have a table which have several columns, right? You will have SW here, you will have RO, you will have RT. This is basically, I should say just R, maybe resistivity, because my first data point is RO. The rest are RT values that you have on that table, right? Okay, so then you can calculate RT. My first data point would be RO, however, right? So this is, let's call this just R. This is going to be RT, and so on and so forth. And then for each of these, you can calculate IR, right? So IR for the first data point is 1, for the second 1.301. Just do a calculation and see if you can get the same number. For the third case, you will get 1.752, and so on and so forth. Okay, so try to see if you can get the same number. Now, next thing is to go to Excel, plot a log plot of your resistivity index IR as a function of water saturation and fit an equation to it, right? Remember what we talked about it in previous slides. If you plot RT over RO, which is the resistivity index, as a function of water saturation, the slope of that line is N, right? And that's the goal here. We want to find that slope, right? So you put your data points, you plot a line, you calculate the slope, and you should get a value of 2.4 for this. So your water saturation exponent is 2.4, and that's what the problem is asking us to calculate, right? And that's it. So we will have one more video for the resistivity, which is going to be a short video on the effect of different parameters on these resistivities.